Hello everyone, my name is Gao Yiqing. I'm a second-year PhD student from ENS Lyon, France. Today I will present our work, which name is Energy Award Strategies for Reliability-Oriented Real-Time Task Allocation on Heterogeneous Platforms. I would like to give my talk as following. At first, I will give the definition of our problem, and then I will present the model of our problem, such as the algorithm we proposed. After that, I will show the simulation result, which shows the performance of our algorithm. Finally, I will conclude our work and discuss what we can do in the future. Here is the definition of our problem. In this work, we found a mapping scheduling solution for a set of real-time independent tasks on a heterogeneous and possibly unrelated platform, which minimizes the expected energy consumption while enforcing the reliability threshold and meeting all task deadlines. Now, let me present the model and the heuristic we use to solve the problem. The platform consists of m heterogeneous processors and a set of n periodic atomic independent tasks. Each task τ(i) has a worst-case execution time Cik on the processor Mk. The worst-case execution times among different processors are not necessarily related. The actual execution times of the tasks are usually lower than their worst-case execution times. The tasks have a common period P, which is equal to their deadline. The energy consumption is different for each processor and includes two parts, static part and dynamic part. The static energy is consumed while it is switched on, no matter if it is currently executing a task. The dynamic energy is consumed while the processor is executing a task. For example, here is the calculation of dynamic energy consumption when task τ(i) executes on processor Mk. We consider transient faults modeled by an exponential distribution of rate lambda k on processor Mk. Fault rates differ from one processor to another. The reliability of task τ(i) on processor Mk with worst-case execution time Cik is calculated as this equation. During the mapping phase, each task will have several replicas executing on different processors in order to match a reliability threshold Ri. Thus, for each task, the probability that at least one replica can successfully finish, which is calculated with this equation, must be larger than Ri. Then we can conclude that the objective of our heuristic is to determine for each task a set of replicas which are executed on a set of different processors and to build a schedule for each processor so that the expected energy consumption is minimized while matching the deadline P and the reliability threshold Ri for each task τ(i). The optimization problem is obviously NP-hard. Due to lack of time, the proof can be found in the paper. Now let me present our heuristic of mapping and scheduling. Firstly, in the mapping phase, we need to define the number of replicas for each task, as well as the execution processor for every replica, aiming at meeting the reliability target while minimizing the energy cost. We first order the tasks according to one of the following criteria. They are in fact all related with the worst-case execution time, as this is the only information that we know about our tasks. In addition, we add also the random criteria as reference. And then, for each task in the ordered list, we order the processors for mapping its replicas according to one of the following criteria. We have increasing energy cost, decreasing reliability, and the ratio of reliability to energy. It takes into account at the same time the two conditions above. We added also the random criteria this time. While the reliability target Ri is not reached, we add replicas for task Tor in the order of the processor list. But we will skip one processor if it is already full. After that, we can obtain our mapping. Then we pass to the schedule phase. In this step, we will order the replicas mapped on each processor to minimize the energy consumption during execution. At first, like in the mapping phase, we order the tasks according to one of the following criteria. They are decreasing increasing number of replicas, decreasing increasing total utilization, which is the sum of the ratio of worst-case execution time to the period for all replicas of task Tor. And then we have also random criteria. After that, for each task in the ordered list, we identify a primary replica according to one of these two criteria, time and energy, and then schedule it as soon as possible. Then, all its other replicas will become secondaries. In a round-robin fashion and in the inverse order of the task list used for the primary, we schedule the secondary replicas, if they exist, as late as possible. For each task, we also have these two criteria, time and energy, to order their secondaries. This scheduling heuristic has objective to avoid overlap between different replicas because the successful execution of one replica leads to the immediate cancellation of all the remaining replicas for the same task. Now we have a multi-criteria heuristic for mapping and for scheduling. Then I will present the result, which shows the performance of our different strategies. At first, let me present the parameter sets we use. In the experiment, we have 10 processors and 20 tasks, which have all the same period, 100. We use CIK to note the worst-case execution time of task Tor on processor MK. The worst-case execution time values are controlled by the correlation factor between the different tasks and between the different processors. We also define a parameter basic work, which is the estimation of the fraction of time that the platform is used if each task has a single replica. It can help us to study the impact of system pressure. We use beta BW to generate the actual execution time WIK for tasks from their worst-case execution times. For each processor MK, we fix the static power PKS, but for the dynamic power, the failure rate, and the reliability target, we have two sets of parameters. The first set is a set of values similar to the previous paper, in which we have a relatively large power and a very small failure rate. And the second set of parameters help us to evaluate our heuristics in the context when failures occur more frequently, where the replicas have a smaller power and a larger failure rate. Now I will present the results of our experiments. Due to lack of time, I will only show the results about large failure rate set, and only a part of parameters which show representative results will be presented here. In the result, we will compare the strategies that we designed with a lower bound established. The lower bound is just a theoretical value and cannot be reached in the real experiment. Each result is represented as a ratio to a random baseline method, which is defined as following. In the mapping phase, for each task, we will add replica randomly on available processors until reaching its reliability target. In the scheduling phase, we will randomly order replicas mapped on each processor and execute them in sequence and as soon as possible. Each point on the graph is an average of 1,000 experiments randomly generated. At first, in this table, we calculated the ratio of different mapping and scheduling ordering tasks criteria. We can see that all criteria for ordering tasks perform equally well. Hence, these criteria do not critically influence energy consumption. Thus, in the following results, we will focus on selecting processors strategies during the mapping phase and on choosing primary and secondary replicas during the scheduling phase. This figure shows results when processor coloration varies. We found that our strategies consume less than 25% of the energy needed by the baseline strategy when correlation processor equals to 0, and the result is close to the lower bound. This value increases with correlation processor, but is always close to the lower bound. For the mapping phase, we can see that in all cases, DEP performs better than or similar to the best strategy between DER and INE. For the scheduling strategies, the figure shows that there is little difference between our different criteria, excepted the random one. This means that our primary-secondary choosing criteria performs well. But we can also observe that with correlation processor not equals to 1, we have energy criteria for primary replica choosing slightly better than time, and when correlation processor equals to 1, the energy becomes worse than time. This figure presents the results when beta BW varies. We observe that for almost all the mapping and scheduling criteria, the results are similar whatever the value of beta. We know that when beta is small, actual execution times can greatly differ from the worst-case execution times used for mapping and scheduling. However, in this case, our heuristics still have a performance similar to that of the lower bound, which shows that they are very robust. From this figure, we can observe the performance of different criteria when varying basic work and reliability target. In the first row of figure, we can see the case of correlation processor equals to 0.5, which is an example of the cases where correlation processor is not close to 1. And in the second row, we can see the case of correlation processor equals to 1. During the mapping phase, we can observe once again DEP, which uses the ratio of reliability to energy, performs the best. For the scheduling phase, we can also find similar performance on all our criteria, except the random, which do not use the primary-secondary strategy. And we can also observe that there is little difference between our strategies and the lower bound. We have a difference of 10% in the worst case. In summarizing all our results, we can find that our strategies can save more than 40% of the energy consumed by the baseline, except in the high processor correlation case. The ratio can be as low as 20% in the best case. For the different criteria used in the heuristics, we find that DEP method is the best processor ordering strategy during the mapping phase. And for scheduling, we can find from the result that all our primary-secondary choosing criteria have a good result, which is close to the lower bound. But we can still find that the two criteria using time when choosing primary replicas performs better when correlation processor is near 1, and energy primary replicas choosing criteria has better performance in other cases. For these best heuristics that we found, the performance is only 17% higher than the lower bound in the worst case. Furthermore, we have a median value of only 3.5 higher than that of the lower bound, and the average value is only 4.3% higher. We can confidently conclude that our best strategies perform remarkably well over the whole experimental setting. In conclusion, in this work, we have studied the problem of executing periodic real-time tasks on a heterogeneous platform with several objectives: minimizing the energy consumption, guaranteeing some reliability thresholds, and meeting all deadlines. For each task, we decide how many replicas should be launched, on which processors to map them, and when to execute them. Extensive simulations show that our best heuristics always achieve good performance, which is very close to the lower bound. For the future work, we can extend the heuristic to periodic graphs of tasks instead of independent task sets. The dependence between tasks will dramatically complicate the mapping and scheduling problems. That's all for my talk. Thank you very much for your listening.